December 19th, 1943, Kwajalein Atoll, Marshall Islands. A single M4 Sherman medium tank sat abandoned on the coral beach, its American crew having retreated under overwhelming Japanese fire just hours before the island's fall. The tank bore serial number 3056289 and belonged to the United States Marine Corps. Though damaged by multiple hits from Japanese anti-tank guns, its armor remained largely intact, its turret still rotated, and most critically, its internal mechanisms lay exposed for examination. Within weeks, Japanese engineers would transport this tank to Tokyo, and what they discovered inside would shatter every assumption they held about American industrial warfare. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The Sherman represented more than a fighting vehicle. It embodied a complete revolution in how modern nations approached mechanized warfare. Over the following 18 months, Japanese tank designers and military engineers would dismantle, measure, and test every component of this machine. The conclusions they reached would prove more devastating than any battle loss, revealing that Japan had entered a war it could never win through industrial means alone. The tank was not superior because of thicker armor or a more powerful gun. It was superior because American factories could produce 50 Shermans in the time Japanese factories struggled to complete one medium tank. The capture occurred during the fierce fighting for Kwajalein in late 1943. American forces had landed on the atoll as part of Operation Flintlock, bringing with them a small number of Sherman tanks to support the infantry assault. The Japanese defenders, heavily fortified and determined to fight to the last man, managed to disable several American vehicles before being overwhelmed. Among the disabled vehicles was this particular Sherman, which had thrown a track after striking a concealed anti-tank mine. Unable to recover the immobilized tank under heavy fire, American forces withdrew, planning to retrieve it after securing the island. They never got the chance. Japanese forces, recognizing the intelligence value of an intact American tank, organized an immediate recovery operation. Under cover of darkness, engineers used captured construction equipment to drag the 29-ton vehicle to a more secure location inland. Within days, as American forces prepared their final assault on the atoll, Japanese command made the decision to evacuate the tank rather than allow it to be recaptured. Using a commandeered cargo vessel, they transported the Sherman first to Truk Lagoon, then northward to Japan itself. The journey took nearly 3 weeks, with the vessel dodging American submarines and patrol aircraft. By late January 1944, the Sherman arrived at Yokosuka Naval Base south of Tokyo. From there, it was transported by rail to the Japanese Army Technical Research Institute at Rikugun Gijutsu Kenkyujo in western Tokyo. This facility, comparable to the American Aberdeen Proving Ground, served as Japan's primary center for evaluating and developing armored fighting vehicles. The arrival of an intact Sherman caused immediate excitement among Japanese tank designers who had only seen distant photographs and read fragmentary intelligence reports about American armor. Major Tomio Hara of the Imperial Japanese Army Ordnance Department took charge of the evaluation. Hara had studied mechanical engineering at Tokyo Imperial University before joining the army, and he had been instrumental in developing Japan's Type 97 medium tank. He assembled a team of Japan's most experienced tank engineers, including specialists in armor metallurgy, automotive engineering, weapons systems, and manufacturing processes. Their mission was clear: determine how the Americans had created a tank that appeared in such overwhelming numbers across every theater of war. The examination began with external assessment. The Sherman measured just over 19 feet in length, 9 feet in width, and stood 9 feet tall. Weight was estimated at 30 tons in combat configuration. Japanese engineers immediately noted that these dimensions made the Sherman significantly larger than Japan's own Type 97 Chiha medium tank, which weighed only 15 tons. The size difference alone suggested vastly greater industrial capacity building, and transporting 30-ton vehicles required infrastructure that Japan had never developed. The armor protection proved the first major revelation. Using portable hardness testing equipment, metallurgists examined the Sherman's armor plate at dozens of points across the hull and turret, The frontal armor measured 2 inches thick, sloped at 56 degrees from vertical. Side armor measured 1.5 inches. The armor was rolled homogeneous steel, hardness tested at approximately 240 Brinell. What astonished Japanese engineers was not the thickness or hardness, both of which fell within expected parameters for a medium tank. What astonished them was the consistency. Hardness readings varied by less than 5% across the entire vehicle. Plate thickness remained uniform within tolerances of a few thousandths of an inch. This consistency could only result from highly controlled industrial processes, automated rolling mills, precise heat treatment facilities, and rigorous quality control systems. Japanese armor plate production, by contrast, showed significant variation in both hardness and thickness. Each plate required individual inspection and often needed adjustment during tank assembly. The Sherman's armor suggested that American steel mills could produce armor plate so consistently that each piece was effectively identical to every other piece from the same production run. The welding proved equally revealing. Japanese engineers examined hundreds of welds joining armor plates throughout the vehicle. Every weld showed consistent penetration depth, uniform bead appearance, and identical heat-affected zones. This consistency indicated the use of standardized welding procedures, possibly semi-automated welding equipment, and welders trained to identical standards across different factories. Japanese tank production relied on master welders whose individual techniques varied. No two Japanese tanks showed identical welding characteristics because each was effectively hand-built by different craftsmen. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The suspension system provided the next major insight. The Sherman used a vertical volute spring suspension system, a relatively simple design consisting of 3 bogie assemblies per side, each with 2 road wheels. Japanese engineers removed the suspension components for detailed examination. Each bogie assembly consisted of 2 vertical volute springs, mounting brackets, wheel arms, and the road wheels themselves. What immediately struck the examining engineers was that every component appeared to have been manufactured to identical specifications. When engineers measured the springs, they found that each spring had identical wire diameter, identical coil spacing, and nearly identical spring rates. This uniformity meant that suspension components were truly interchangeable. Any spring could replace any other spring on any Sherman tank. The implications were profound. If a Sherman threw a track and damaged a suspension bogie in combat, field mechanics could replace the entire assembly in under an hour using standard replacement parts. No fitting, no adjustment, no modification required. Japanese tanks, with their individually fitted components, required skilled mechanics and often several hours of adjustment even for simple repairs. The road wheels themselves told a similar story. Each wheel was a cast steel assembly, machined on the mounting surface and bearing races. Japanese engineers measured dimensional tolerances on multiple wheels. Every wheel measured identical to within 0.02 of an inch on critical dimensions. The wheels were not just similar, they were functionally identical, clearly produced on automated machinery set to precise specifications. Japanese tank wheels were cast individually and then hand-machined, with each wheel requiring final fitting to its specific mounting point. The tracks revealed perhaps the most dramatic evidence of American mass production capability. Sherman tracks consisted of 79 individual track links per side, each link a steel casting with machined bearing surfaces. Engineers removed several track sections and examined individual links under magnification. Every link showed identical casting characteristics, the same surface finish, the same internal structure visible on broken samples, the same dimensional accuracy. When engineers measured the pinholes on 50 random track links, they found dimensional variation of less than 0.005 of an inch. This uniformity had practical implications that Japanese officers immediately understood. Sherman tracks could be repaired in the field by replacing individual damaged links. Any link from any Sherman would fit any other Sherman. Crews could even salvage usable links from destroyed tanks to repair damaged vehicles. Japanese tank tracks, being less precisely manufactured, often required replacing entire track sections rather than individual links because dimensional inconsistencies prevented reliable interchange. The powertrain provided even more sobering revelations. Engineers carefully documented the process of removing the Sherman's engine, a Wright Continental 975-cone radial aircraft engine adapted for tank use. The engine produced 400 horsepower and displaced 975 cubic inches. What struck Japanese engineers immediately was that this was fundamentally an aircraft engine, designed for mass production and installed in a tank with minimal modification. The engine removal process itself proved instructive. 4 men could remove the entire engine in approximately 3 hours using basic tools. The engine was mounted on a sliding frame that pulled out through the rear of the hull once external connections were disconnected. This design allowed complete engine replacement in field conditions without specialized equipment. Japanese tanks required partial disassembly of the vehicle to access major engine components, and engine replacement typically took several days even under ideal conditions. When engineers disassembled the radial engine, they discovered a level of manufacturing precision that shocked them. The engine consisted of 9 cylinders arranged radially around a central crankcase. Each cylinder was a separate assembly that bolted to the crankcase. Engineers measured critical dimensions on multiple cylinders. Bore diameter varied by less than 1/1000th of an inch between cylinders. Piston-to-cylinder clearances measured identically across all 9 cylinders. The crankshaft, a massive forged component, showed machining precision that Japanese engineers had only seen in the finest aircraft engines. But the most disturbing discovery came when engineers examined the engine's manufacturer markings and production data. The data plate indicated this particular engine had been manufactured in August 1943 at Continental Motors in Detroit, Michigan. Quick calculation revealed that this engine had been built, installed in a tank, shipped across the Pacific Ocean, and deployed in combat, all within approximately 4 months. This production-to-deployment timeline suggested an industrial system operating at a scale that Japanese factories could never approach. The transmission system provided further evidence of systematic American engineering. The Sherman used a synchromesh transmission with 5 forward gears and 1 reverse gear. Japanese engineers had limited experience with synchromesh transmissions. Most Japanese tanks used simpler crash box transmissions requiring double clutching for gear changes. The Sherman's transmission allowed smooth gear changes without extensive driver training, effectively democratizing the skill required to operate the vehicle. Engineers disassembled the transmission completely, laying out hundreds of gears, shafts, bearings, and synchronizer assemblies. Measurements revealed that every gear was cut to tolerances typically associated with precision machinery. Gear teeth showed identical profiles across multiple gears. Bearing races were ground to mirror finishes. Synchronizer cones showed precisely machined tapers. The transmission represented hundreds of hours of precision machining, yet American factories were installing these transmissions in tanks at the rate of dozens per day. The final drive and differential assemblies showed similar precision manufacturing. These components transmitted power from the transmission to the drive sprockets that moved the tracks. Japanese engineers found that every component was designed for quick replacement. The entire final drive assembly could be unbolted and removed as a unit, allowing field replacement of a damaged final drive in approximately 2 hours. Japanese tank final drives required partial disassembly of the vehicle and often a full day of work to replace. The turret and armament systems provided insights into American weapons manufacturing. The Sherman mounted a 75mm M3 medium-velocity gun, not the most powerful tank gun in service by 1944, but more than adequate against most targets. Japanese engineers examined the gun and its mounting carefully. The gun itself was a relatively simple design, optimized for mass production rather than maximum performance. The barrel was manufactured by drilling and reaming solid steel billets, a process that could be automated. The gun's recoil mechanism demonstrated sophisticated hydraulic engineering. The mechanism used a combination of hydraulic buffer and spring recuperator to absorb recoil and return the gun to battery. Engineers disassembled the recoil mechanism and found precision-machined components throughout. Hydraulic cylinders were honed to mirror finishes. Seals were precision-molded rubber rather than handmade leather. The entire mechanism could be removed and replaced as a unit, with replacement mechanisms stored in standardized containers designed for field deployment. The guns mounting in the turret used a gyro stabilizer system, a sophisticated mechanism that kept the gun approximately on target even as the tank moved across rough terrain. This stabilization system represented advanced engineering that Japan had not attempted in any of its tanks. Engineers examining the gyro stabilizer found it consisted of gyroscopes, electric motors, hydraulic actuators, and electronic control circuits. Every component showed evidence of mass production, standardized electronic components, machine-crimped electrical connections, and modular assemblies designed for replacement rather than repair. The fire control system included a periscopic gun sight, a telescopic sight, and a simple mechanical ballistic calculator. While not exceptionally advanced, these systems were well integrated and designed for use by crews with moderate training. Japanese tank sights were often individually calibrated precision instruments requiring skilled gunners. The Sherman's sights were robust, mass-produced devices that any adequately trained gunner could use effectively. The electrical system throughout the Sherman demonstrated systematic American engineering. Every wire connection used standardized terminals crimped by machine. Circuit breakers protected major electrical components. The wiring harness was organized with color-coded wires and numbered connection points. Any electrician with basic training could trace circuits and replace components using the technical manuals. Japanese tank electrical systems typically required skilled electricians who understood the specific vehicle they were working on. The ammunition storage demonstrated practical design thinking. The Sherman carried 90 rounds of 75mm ammunition stored in racks throughout the hull and turret. Each round was held in a spring-loaded clip that released when pulled. Crew members could access ammunition quickly without specialized tools. The design prioritized speed of access, and safety ammunition was stored low in the hull to reduce fire risk. Japanese tanks often stored ammunition in less accessible locations, requiring crews to handle rounds awkwardly during combat reloading. The crew accommodations revealed American attention to human factors. The Sherman's interior provided relatively spacious accommodations for its 5-man crew: commander, gunner, loader, driver, and assistant driver. Seats were adjustable and padded. Controls were logically arranged and clearly labeled. Vision blocks provided good visibility. The design recognized that crew efficiency directly impacted combat effectiveness, and that well-rested, comfortable crews performed better over extended operations. Japanese engineers noted that their own tanks provided far more cramped accommodations. The Type 97 Chiha medium tank, Japan's most common tank, crammed 4 men into a space considerably smaller than the Sherman's interior. Japanese tank designers had prioritized armor protection and mechanical simplicity over crew comfort, assuming that discipline and fighting spirit would compensate for physical discomfort. The American approach suggested a different philosophy, that effective combat performance required supporting the crew with well-designed equipment. By spring 1944, Japanese engineers had completed their detailed technical examination of the captured Sherman. They had measured thousands of components, documented manufacturing methods, analyzed metallurgy, and tested every system. The technical data filled dozens of reports. Photographs documented every major component. Technical drawings showed critical assemblies. The information was distributed to Japanese tank designers and military planners. But beyond the technical specifications lay a more disturbing realization. The Sherman was not a superior tank because of any single advanced feature. Its armor was adequate, but not exceptional. Its gun was effective, but not the most powerful. Its engine was reliable, but not particularly innovative. The Sherman was superior because it represented a complete industrial system designed for mass production. Every component showed evidence of systematic engineering focused on manufacturability, maintainability, and interchangeability. Japanese engineers calculated production requirements with growing alarm. Each Sherman contained approximately 18,000 individual parts when accounting for every bolt, rivet, wire, and component. Manufacturing these parts to the precision levels observed required specialized machinery, automated lathes, milling machines, grinding equipment, hydraulic presses, and heat treatment facilities. American factories possessed this equipment in quantities that Japanese industry had never approached. The Wright radial engine alone contained over 2,000 precision-machined components. Continental Motors, the engine manufacturer, was primarily an automobile engine company that had adapted its production lines to manufacture aircraft and tank engines. This adaptability revealed something profound about American industrial organization. Companies could redirect their manufacturing capability toward war production because their fundamental production methods, precision machining, automated assembly, standardized components applied across different products. Japanese aircraft engine manufacturers were specialized facilities that had developed expertise in building specific engine types. They could not easily shift to producing different engines because their production methods relied on skilled workers who knew particular engines intimately. American production methods relied on precision machinery and systematic processes that could be applied to new products by training workers in new procedures rather than new crafts. Major Hara prepared a comprehensive report for the Army Technical Bureau in May 1944. His report documented every technical finding in meticulous detail, but the final section addressed the question that haunted every engineer who had examined the Sherman. How many of these tanks could America produce, and could Japan match that production? The evidence suggested devastating answers. The Sherman's design prioritized production speed over maximum performance. Its armor was adequate rather than maximum. Its gun was effective rather than the most powerful available. Its mechanical systems favored reliability and ease of maintenance over ultimate efficiency. Every design choice reflected an industrial strategy focused on producing large quantities of good enough tanks rather than small quantities of perfect tanks. Japanese intelligence estimated that American factories had produced approximately 10,000 Sherman tanks by early 1944. This number seemed almost impossible. Japan's entire tank production from 1937 through 1943 totaled fewer than 4,000 tanks of all types. America was producing more tanks in a single year than Japan had produced in 7 years of war and preparation. The production methods visible in the Sherman's construction explained how such output was possible. If every component was precisely manufactured to allow interchangeable assembly, then assembly lines could operate continuously without stopping for fitting and adjustment. If workers needed only basic training because precision was built into the tooling rather than the craftsman's skill, then factories could expand production by hiring and quickly training new workers. If field maintenance required only standard replacement parts rather than skilled modification, then more tanks remained operational rather than awaiting repair. Japanese tank production faced opposite conditions at every point. Skilled workers remained in short supply, and training new craftsmen to required skill levels took years. Components required individual fitting during assembly, slowing production. Field maintenance demanded highly trained mechanics who could modify parts to fit specific vehicles. Increasing production meant finding and training more skilled workers, not simply adding more assembly stations. Lieutenant Colonel Tadashi Takashima, Chief of Tank Development at the Army Technical Bureau, reviewed Hara's report with growing concern. Takashima had overseen development of Japan's latest medium tank, the Type 3 Chi-Nu, which mounted a more powerful 75mm gun than the Sherman. On paper, the Chi-Nu appeared competitive with American armor. In practice, Japan would produce fewer than 200 Chi-Nu tanks before the war ended, while American factories would ultimately produce over 49,000 Shermans. Takashima understood that the comparison was not between tanks but between industrial systems. The Chi-Nu represented the best that Japanese craftsmen could produce using traditional manufacturing methods. The Sherman represented what American industry could produce using systematic mass production. In a war of attrition, craft production could never compete with mass production regardless of individual product quality. The Japanese Army initiated efforts to implement American-style production methods in mid-1944. Engineers who had examined the Sherman were assigned to major tank factories with instructions to modernize production processes. The Mitsubishi plant at Tokyo, primary producer of the Type 97 Chiha medium tank, received particular attention. American production methods required machine tools that Japanese factories did not possess in sufficient quantities. Precision lathes, automated milling machines, hydraulic presses capable of forming large panels, all were in short supply. Japan's machine tool industry had never developed capacity comparable to American or German manufacturers. Even when appropriate machinery could be found or manufactured, implementing new production methods proved difficult. Factory workers who had spent years developing craft skills resisted changes that seemingly devalued their expertise. Supervisors who had organized production around skilled craftsmen struggled to reorganize around systematic processes. Engineers who had designed tanks for craft production found it challenging to redesign for mass production. The captured Sherman became a teaching tool. Selected factory supervisors and senior craftsmen were brought to Tokyo to examine the American tank. Engineers demonstrated how standardized components allowed rapid assembly. They showed how interchangeable parts simplified field maintenance. They explained how precision manufacturing at the component level eliminated the need for skilled fitting during assembly. Some workers grasped the implications immediately. Others remained skeptical that machines could replace human skill. By late 1944, American strategic bombing began targeting Japanese industrial facilities with increasing intensity. Boeing B-29 Superfortress bombers, operating from bases in China and later the Marianas, struck aircraft factories, engine plants, and steel mills. Tank production facilities suffered collateral damage even when not directly targeted. The bombing campaign destroyed any realistic hope of modernizing Japanese tank production during wartime. The Mitsubishi tank plant at Tokyo was partially destroyed in an air raid in November 1944. Production dropped immediately from approximately 40 tanks per month to fewer than 20. Repair efforts consumed resources that might otherwise have supported production expansion. By early 1945, the plant was operating at less than half capacity, and even that limited production relied increasingly on salvaged components and improvised materials. Japan's steel industry faced similar devastation. American submarines had effectively cut maritime shipping by late 1944, choking off iron ore imports from China and Southeast Asia. Domestic steel production, never sufficient for wartime needs, fell dramatically as raw materials grew scarce. Tank armor plate, requiring specific steel alloys and careful heat treatment, became increasingly difficult to produce. Quality control suffered as experienced metallurgists were drafted or killed in air raids. The final Japanese tank designs of the war showed both the influence of examining the Sherman and the impossibility of implementing the lessons learned. The Type 4 Chi-2 medium tank, designed in 1944, incorporated a more powerful 75mm gun and thicker armor than previous Japanese tanks. Engineers attempted to implement some standardization in component design, but fewer than 6 Chi-2 tanks were completed before the war ended. The design existed, but the industrial system to produce it did not. The Type 5 Shirei medium tank, Japan's most advanced tank design, reached prototype stage in 1945. It mounted a formidable 75mm gun and incorporated sloped armor, influenced by both the Sherman and captured Soviet 34 tanks. The design showed that Japanese engineers understood modern tank requirements, but understanding requirements and possessing the industrial capacity to meet them were different things entirely. Only one Shirei prototype was completed. Meanwhile, American tank production continued accelerating. By 1945, multiple factories across the United States were producing Shermans, as well as improved variants mounting more powerful guns and heavier armor. The M26 Pershing heavy tank entered production, providing American forces with armor comparable to German heavy tanks. American industry demonstrated the ability not just to produce tanks in quantity, but to continuously improve designs while maintaining production volume. Japanese officers studying intelligence reports tracked American tank deployment with deepening despair. Sherman tanks appeared in overwhelming numbers on every front. In the Philippines, on Iwo Jima, on Okinawa, everywhere American forces landed, Shermans provided armored support that Japanese forces could not match. Japanese anti-tank weapons, designed to defeat lighter armored vehicles, proved less effective against the Shermans' frontal armor. Even when Japanese guns disabled Shermans, American recovery teams quickly repaired or replaced damaged vehicles. The asymmetry became most apparent in maintenance and logistics. American armored units kept high percentages of their tanks operational because field maintenance required only standard replacement parts and moderate mechanical skill. Japanese tanks, requiring skilled mechanics and often custom-fitted parts, spent increasing time deadlined for maintenance. As the war progressed and skilled mechanics were killed or wounded, Japanese tank readiness rates declined steadily. Captain Masanori Watanabe, a tank company commander who fought on Luzon in early 1945, later described the psychological impact of facing Sherman tanks in overwhelming numbers. His company deployed with 12 Type 97 Chiha medium tanks, Japan's most common tank. In the first engagement with American armor, his company destroyed 2 Shermans using carefully planned ambushes. Within hours, American forces counterattacked with 15 Shermans, overwhelming his positions through sheer numbers and superior firepower. Watanabe's remaining tanks retreated into prepared defensive positions. Over the following week, he watched as American recovery teams salvaged the 2 destroyed Shermans. Within days, both tanks were back in service with replacement turrets and repaired hulls. Meanwhile, 3 of his own tanks remained immobilized with mechanical problems that his mechanics lacked parts to repair. The message was clear: America could replace losses faster than Japan could inflict them. The final battles of the Pacific War demonstrated the cumulative advantage of American industrial superiority. On Okinawa, American forces deployed over 800 tanks and armored vehicles against Japanese defenders who possessed fewer than 30 operational tanks. The numerical advantage alone was crushing, but the qualitative advantage in maintenance, logistics, and operational readiness multiplied the disparity. Japanese tanks that broke down stayed broken down. American tanks that suffered damage were often back in service within hours. After Japan's surrender in August 1945, American technical intelligence teams examined Japanese tank production facilities. What they found confirmed the assessments that Japanese engineers had reached through examining the captured Sherman. Japanese factories were organized for craft production, not mass production. Skilled workers hand-fitted components that American factories would have produced to interchangeable tolerances. Quality control relied on experienced craftsmen rather than systematic measurement and testing. The United States Strategic Bombing Survey, which conducted comprehensive assessments of Japanese war production, concluded that Japan's tank production never approached the volume required for sustained mechanized warfare. Monthly production peaked at approximately 200 tanks in mid-1944, then declined as resources grew scarce and bombing intensified. American monthly tank production exceeded 2,000 vehicles during the same period, a 10-to-1 advantage that no amount of tactical skill or fighting spirit could overcome. American engineers touring the Mitsubishi tank plant observed production methods that seemed decades behind American practices. Workers hand-formed armor plates that would have been die-stamped in American factories. Welders individually crafted joints that American factories produced with semi-automated welding equipment. Assembly proceeded sequentially as craftsmen fitted components to each specific vehicle, rather than on moving assembly lines with interchangeable parts. The survey team noted that Japanese tank designers clearly understood modern requirements. Their latest designs incorporated sloped armor, powerful guns, and sophisticated sighting systems. The problem was not design knowledge but production capability. Japanese factories could produce sophisticated prototypes. They could not produce thousands of tanks to any design, sophisticated or simple. The industrial infrastructure for mass production simply did not exist. Japanese engineers who had examined the captured Sherman recognized these conclusions as validating their own assessments. They had understood, as early as 1944, that Japan had entered an unwinnable war of industrial attrition. The Sherman tank had taught them that modern warfare belonged not to the nation with the most skilled craftsmen, but to the nation with the most effective industrial systems. The lesson came too late to change the war's outcome, but it would profoundly influence Japan's post-war reconstruction. The transformation of Japanese manufacturing from craft-based production to systematic mass production began not in factories, but in the minds of engineers who had spent months examining American equipment. These men understood that Japan's post-war survival depended on learning the lessons that wartime necessity had prevented them from implementing. The captured Sherman tank, destroyed along with most war records in the final months of conflict, had nevertheless planted seeds that would reshape Japanese industry over the following decades. In the immediate post-war years, Japan's industrial capacity lay in ruins. American bombing had destroyed approximately 40% of urban industrial areas. Machine tools were worn out or damaged. Skilled workers had been killed in combat or air raids. Raw materials remained scarce as the nation struggled to feed its population and rebuild basic infrastructure. Yet within this devastation, a small group of engineers and industrial planners began laying groundwork for transformation that would eventually make Japan one of the world's leading manufacturing nations. Major Tomio Hara, who had led the technical evaluation of the captured Sherman, survived the war and joined the Ministry of International Trade and Industry in 1949. His wartime experience examining American manufacturing methods influenced his approach to industrial policy. Hara understood that rebuilding Japanese manufacturing required more than repairing damaged factories. It required fundamentally rethinking how products were designed and produced. The American occupation authorities, initially focused on demilitarizing Japanese industry, gradually shifted toward rebuilding Japan as a bulwark against communist expansion in Asia. This policy shift opened opportunities for Japanese engineers to study American manufacturing methods directly. The occupation forces brought American industrial advisors who introduced quality control methods, production management techniques, and manufacturing engineering principles that few Japanese factories had implemented before the war. W. Edwards Deming, an American statistician and quality control expert, delivered a series of lectures to Japanese engineers and executives in 1950. Deming's message resonated powerfully with engineers who had examined the captured Sherman. He taught that quality resulted not from skilled craftsmanship inspecting finished products, but from systematic control of production processes. Quality should be built into manufacturing through statistical process control, standardized procedures, and continuous improvement. These principles aligned perfectly with what Japanese engineers had observed in the Sherman's construction. Precision came from the production system, not individual craftsmen. Japanese companies embraced Deming's teachings with enthusiasm that surprised even Deming himself. Engineers, who had seen American mass production firsthand during the war, understood that these methods represented the future of manufacturing. They became evangelists within their companies, advocating for systematic approaches that initially met resistance from traditionalists who valued craft skills and individual expertise. The Toyota Motor Company provided the most dramatic example of transformation. Kiichiro Toyoda, the company's founder, had visited American automobile factories before the war and recognized the superiority of American production methods. His cousin, Eiji Toyoda, traveled to the United States in 1950 to study Ford Motor Company's River Rouge plant, at that time the world's largest and most integrated automobile factory. Eiji Toyoda spent 3 months at River Rouge, observing every aspect of Ford's production system. He saw automated stamping presses forming body panels, automated paint lines, and moving assembly lines where standardized components were, installed by workers performing repetitive tasks. The scale was staggering. Ford was producing 7,000 vehicles per day, while Toyota's entire annual production was approximately 3,000 vehicles. Yet Toyota also observed inefficiencies in the American system, excess inventory, wasted motion, and quality problems that required extensive rework. Returning to Japan, Toyota worked with production engineer Taiichi Ono to develop what became the Toyota production system. This system adapted American mass production principles to Japanese conditions while improving on aspects that Toyota had identified as wasteful. The fundamental insight came from the wartime examination of American equipment like the Sherman tank, Precision manufacturing of interchangeable components enabled efficient assembly, but Toyota added innovations that reduced waste even further. The just-in-time production method ensured that components arrived at assembly stations exactly when needed, eliminating inventory waste. G-DOCA, or automation with a human touch, empowered workers to stop production lines when defects appeared, preventing defective components from proceeding through assembly. Continuous improvement, or Kaizen, made every worker responsible for identifying and eliminating inefficiencies. These additions transformed American-style mass production into something more flexible and efficient. By the mid-1950s, Toyota was producing vehicles with quality and efficiency that began approaching American standards. The company's Corona model, introduced in 1957, demonstrated that Japanese manufacturers could produce reliable automobiles using systematic production methods. More importantly, Toyota's success demonstrated to other Japanese manufacturers that transformation from craft to systematic production was possible. Other Japanese companies followed similar paths. Matsushita Electric, which would later become Panasonic, sent engineers to study American consumer electronics manufacturing. They observed how American companies used automated assembly equipment, standardized components, and modular design to produce radios and televisions in high volumes. Returning to Japan, these engineers implemented similar methods, adapting American techniques while adding Japanese innovations in miniaturization and quality control. The transformation required more than copying American methods. It required changing fundamental assumptions about manufacturing. Japanese factories had traditionally valued the master craftsman who could coax perfection from imperfect materials and processes. American methods, as embodied in equipment like the Sherman tank, valued systematic processes that produced consistent results, regardless of individual worker skill. Japanese companies had to learn that precision came from the production system, not the craftsman. This cultural shift proceeded gradually over 2 decades. Older workers and managers who had built their careers on craft skills sometimes resisted changes that appeared to devalue their expertise. Younger engineers, many of whom had studied American methods during the occupation or traveled to the United States, pushed for systematic approaches. The tension between tradition and modernization played out in countless factories as Japan rebuilt its industrial base. The Korean War, which began in 1950, provided unexpected impetus for Japanese industrial recovery. American forces required massive quantities of supplies, equipment, and vehicles. Japanese factories received contracts to produce everything from military vehicles to steel products. These contracts provided capital for factory modernization and exposed Japanese manufacturers to American quality standards and production requirements. Meeting American military specifications required implementing systematic quality control and standardized production methods. By the early 1960s, Japanese manufacturers were producing consumer products that competed successfully in international markets. Sony transistor radios, Honda motorcycles, and Toyota automobiles began appearing in American stores. These products competed not through lower prices alone, but through quality and reliability that matched or exceeded American products. The transformation was becoming visible in global markets. The 1960s brought intensive study of American manufacturing by Japanese companies, eager to close the remaining gaps. Hundreds of Japanese engineers traveled to the United States annually, touring factories, attending conferences, and studying at American universities. They returned with knowledge of the latest manufacturing technologies, quality control methods, and production management techniques. This knowledge transfer accelerated Japan's industrial development, but Japanese companies did not simply copy American methods. They adapted and improved them. Toyota's production system reduced inventory waste beyond what American factories achieved. Sony's miniaturization of electronics created products that American companies had not imagined. Honda's approach to engine manufacturing achieved reliability levels that surprised American motorcycle manufacturers. Japanese industry was not merely catching up, it was innovating. The steel industry demonstrated the transformation most dramatically. Japan's post-war steel industry started with obsolete facilities and limited raw materials. By the 1960s, Japanese steel companies were building the world's most modern integrated steel mills, using oxygen furnaces and continuous casting methods that produced higher quality steel with less waste than traditional American mills. Japanese steel began appearing in American construction and manufacturing, valued for its consistent quality and competitive pricing. Shipbuilding showed similar patterns. Japanese shipyards adopted American welding, techniques and production methods, then improved on them. By the late 1960s, Japan had become the world's largest shipbuilding nation, producing vessels faster and more efficiently than American or European yards. The industry that had struggled to produce enough ships during the war now dominated global markets through systematic application of mass production principles. The electronics industry perhaps best exemplified the transformation. Companies like Sony, Matsushita, and Hitachi started by licensing American technology and studying American production methods. Within 2 decades, they were producing consumer electronics that American companies could not match in quality or price. Transistor radios, televisions, and tape recorders bearing Japanese brand names filled American homes by the 1970s. The automobile industry completed the transformation. Toyota, Honda, and Nissan began exporting vehicles to the United States in significant numbers during the 1960s. American consumers initially viewed Japanese cars as cheap alternatives to American vehicles. By the 1970s, that perception was changing. Japanese cars proved more reliable, more fuel efficient, and often better built than American competitors. The 1973 oil crisis accelerated acceptance of Japanese vehicles, and by the 1980s, Japanese manufacturers were building factories in the United States. The irony was not lost on observers who remembered the wartime examination of captured American equipment. Japanese engineers had studied the Sherman tank and other American equipment, learning that systematic mass production could overwhelm craft production through sheer volume and efficiency. They had spent decades implementing those lessons. By the 1980s, American manufacturers were studying Japanese production methods, learning how Toyota and other companies had refined American techniques into even more efficient systems. American automotive executives toured Japanese factories and observed production methods that seemed to operate with almost no waste. Assembly lines moved smoothly with minimal inventory. Quality control was built into every production stage rather than inspected at the end. Workers were empowered to identify and solve problems rather than simply following instructions. These Japanese innovations, built on foundations learned from studying American equipment during the war, now represented best practices that American companies needed to learn. The transformation extended beyond manufacturing to broader industrial organization. Japanese companies developed long-term relationships with suppliers, sharing information and coordinating improvements across entire supply chains. This approach, influenced partly by necessity in resource-poor post-war Japan, created networks of companies working toward mutual benefit rather than adversarial relationships common in American industry. Quality circles, where workers met regularly to identify improvements, became standard practice in Japanese factories. This organizational innovation empowered workers in ways that American factories, with their strict divisions between management and labor, had not imagined. The skilled craftsmen who had once fit components individually now applied their expertise to improving production systems that produced precise components automatically. By the 1980s, Japan had become the world's second-largest economy. Japanese products dominated consumer electronics, automobiles, steel, shipbuilding, and numerous other industries. The transformation from wartime devastation to economic powerhouse took less than 4 decades. The foundation for this success was laid by engineers who had examined captured American equipment during the war and understood that systematic mass production represented the future of manufacturing. The captured Sherman tank, examined in 1944, had taught Japanese engineers that they had entered a war they could not win industrially. More importantly, it taught them why. American success came not from superior designs or better materials, but from systematic organization of manufacturing that enabled production in overwhelming quantities. Components were precisely manufactured to allow interchangeable assembly. Workers needed basic training rather than years of apprenticeship. Field maintenance required standard parts rather than skilled modification. Every aspect of design and production focused on enabling mass production. These lessons, painful during wartime, became the foundation for post-war transformation. Japanese engineers did not forget what they had learned from examining American tanks, aircraft, and other equipment. They carried those lessons into peacetime, applying systematic production methods to civilian manufacturing. They studied American techniques, adapted them to Japanese conditions, and improved on them. The skilled craftsmen who had built wartime equipment became the experts who designed production systems, enabling less skilled workers to produce precise products at scale. The story illustrates a broader truth about industrial competition and technological development. Success comes not from protecting traditional methods, but from learning from competitors and continuously improving. Japanese engineers who examined the Sherman tank could have responded with denial or despair. Instead, they absorbed the lessons and spent decades implementing them. American engineers who later studied Japanese factories could have responded with defensiveness. Many instead learned from Japanese innovations and brought those lessons back to American manufacturing. Manufacturing excellence, whether American mass production of the 1940s or Japanese refined production systems of the 1980s, results from systematic thinking about how to organize human effort and machinery toward consistent output. The Sherman tank embodied systematic American thinking about how to produce complex equipment in quantity. Japanese manufacturers eventually embodied systematic thinking about how to produce quality equipment efficiently. Both approaches taught the same fundamental lesson. Precision must be built into the production system, not dependent on individual craftsman skill. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.